Hello everyone, and welcome to the one-dimensional projectile motion post-lab. So let's start out by going over the graphs that you found in your Pivot Interactive. So here we have a ball. I'm just using a soccer ball, right? And that ball is going to go up and come all the way back down. And then check out what happens as it goes up and down as we draw the position versus time graph, the velocity versus time graph, and the acceleration versus time graph. Now, in order to go with your pivot, I am going to call the highest point 0. The highest point it reaches 0, okay? And everything below that, negatives. So that's why our position time graph is going to be in the 4th quadrant with negative positions. However, you might also see this same kind of thing with the ground being 0, in which case we would be in the 1st quadrant. The graph would look the same in terms of the shape, right? It's just that it would start at 0 and end at 0, right? And go above that positively. But this will look more like what you saw on the pivot. Ready? Now watch that again, because this isn't something you can do in the pivot, right? This is more like we were using, say, a motion detector or something, where we were getting the graphs in real time. Okay, so as it goes up, highest point comes back down. Note here, the highest point is 0. Right? So we get the full parabola this time, as you did in your lab. And this is what your velocity versus time graph looks like. And note, that velocity versus time graph is a linear graph. And therefore, the acceleration is uniform. And since this is negative slope, right, it's a negative constant acceleration. And I think as you found in the lab, right, it was a negative 9.8-ish meter per second every second. So hopefully this is what your 3 graphs look like. And let's watch that one more time. Here we go. Note here that the dotted line represents the highest point, right, that it moves. And so you can kind of see the symmetry on either side. Nudge, nudge, right? And down here. Okay. So this isn't something that I asked you to do on the lab sheet, so you may want to take some notes on this. But this is going to be a motion map for that motion, right? So this is the first dot. This is the 0 time dot, okay? You ready for this? Here we go. Let's watch that one more time. So remember here that a motion map in a uniformly accelerated motion has 3 different parts. It has dots, it has velocity arrows attached to the dots, those are the red arrows here, and then it has acceleration arrows below the dots. Since this is vertical, it's to the side of the dots, right? This is a position reference line, a vertical position reference line. Notice pointing down because down is negative. And so I want you to notice a few things about this. Let's start out by looking at the dots. On the way up, what's happening to the separation between the dots? So let's talk about the way up. Right? The dots are getting closer together. Well, why? Yeah, because it's slowing down. You can also see that in the velocity arrows, because what's happening to them? Yes, the velocity arrows are getting smaller. However, the acceleration arrows are staying the same size because it's a uniform acceleration. But you're going up and slowing down. Note the acceleration arrows point down. They're working against the motion, which means you're slowing down, right? See how this fits all of the patterns we saw for horizontal things? So the dots get closer together, the velocity arrows get shorter, the acceleration arrows point in the opposite direction to the motion. 3 ways for you to see the ball slowing down. Now let's look at the highest point. That's this dot. Now you might notice that rather than put it here, I moved it over here. Why did I do that? Well, because I knew that what was going to happen is it was going to come back down afterwards, and I didn't want this stuff to overlap with the going up stuff. Right? So just like if I was going up and down a hill with a cart, right, I took that highest point and I moved it up a level. Okay? And I'm assuming here that I did this perfectly so that the highest point is one of our times, right? So notice here at the top, there is no velocity arrow. Why? Because at the top, it is instantaneously at rest. Now, it doesn't stay at rest, right? It's just at rest for that one instant. In the pivot, which I really liked, it was that one frame, right? It was doing 1,500 frames every second, but there was only one frame where it was at the top. Prior to that, it was slowly moving upward. After that, it was slowly moving downward, right? But at this point, instantaneously zero velocity. However, it is still accelerating. Well, let's think why. Two reasons. First off, what if it wasn't? What would happen to something with no velocity and no acceleration? Doesn't an object with no velocity and no acceleration just sit there? Right? There's no velocity, so it's not already moving. And if there's no acceleration, that means its velocity isn't changing, since acceleration is the rate of change of velocity. Right? So an unchanging zero velocity means you don't go anywhere. Well, when you threw the ball up in the air, did it stay at that highest point and get stuck there? No. Again, the video did a great job of showing you that it was one frame out of thousands, right, in that video that was actually at the highest point. Right? So no velocity arrow here, but on the way down, so let's start there. And the other reason is there's still a force acting on it here. Right? Gravity is still acting on it, and there's nothing balancing that gravity out since we're neglecting any air resistance effects. That means there's a net force, and net forces result in accelerations. All right, so here's that. And what's happening on the way down? Well, kind of the opposite thing that's happening on the way up. The dots are getting further apart. The velocity arrows are getting longer. And note now the acceleration arrows, which still point down because that gravitational net force always points down, right, are now pointing in the same direction it's moving. Hence, it's speeding up. Right? So 3 ways to tell from the motion map here that it's speeding up on the way down. Dots get further apart. Remember, there's equal times, right, for each dot. So the dots are getting further apart, the velocity arrows are getting bigger, and the acceleration arrows are pointing in the same direction as the object's moving, as the velocity arrows. So a ton going on, right, in this motion map that you can see. And really, it's just a different way of looking at this uniformly accelerated projectile motion, one-dimensional projectile motion, right? Just like the graphs were. They're all just representations. They're not reality, right? The reality was the ball actually going up and down. These are ways to represent the reality. And if you understand the representational tools like the graphs or the motion map, there's a lot you can see about what's happening. Now, a couple other things that you might notice here. Okay? And if we go back to the graphs, as I mentioned, there is some beautiful symmetry, right? And the symmetry is there because the acceleration is uniform. It's constant. So on the way up, the ball is slowing down 9.8 meters per second every second, but on the way down, it's speeding up 9.8 meters per second every second. That means that it is speeding up just as fast as it's slowing down, and that gives us a nice symmetric graph. Note here how the corresponding position dots are at exactly the same height. And then notice, and this one's a little trickier, but you can see it in my drawing, that the velocity arrows, corresponding velocity arrows, are the same length. So we have this weird occurrence where on the way down, the velocity arrows don't fill the whole space. That's because at this point, it's going the same speed as it is at this point. Right? At this dot, it's going the same speed as it was here, just down instead of up, right? The velocities are the same size, but the opposite direction, and here. So a lot of beautiful symmetry if we get the full one-dimensional projectile motion going on here. Symmetry can be your friend in understanding what's going on. We can also see basically it takes the same amount of time to go up as it does to come down, because everything is symmetric. So this is projectile motion that we're looking at, in particular one-dimensional projectile motion, and we've already done the proof, because isn't the force diagram on the way up at the top and on the way down all the same? Right? You wrote that on your lab sheet. It's just the force of gravity. And if the force of gravity is providing our net force, and it's constant, which as long as we don't get far away from the surface of the Earth, it is a constant, right? You weigh the same amount at the top floor of a building as you do at the bottom floor of a building, unless you get really, really, really precise. Right? Then we already did the proof. We know that the acceleration is equivalent to the gravitational field strength, which is negative 9.8 newtons per kilogram near the surface of the Earth, which gives us an acceleration of negative 9.8 meters per second squared near the surface of the Earth. Meters per second every second. Did you see that in your lab? I bet you did. Right? I bet your acceleration was pretty darn close to 9.8. I didn't gather them this time because we had done that in the Freefall one, right? But I bet everybody's was right about 9.8, just like in the Freefall one. And this, of course, is uniformly accelerated motion. You saw a beautiful diagonal linear velocity time graph, right? And that means that the slope, which is the acceleration, is constant. And of course, that means we can use the beautiful kinematic equations. Nothing new here. We already talked about this with Freefall. Again, I switched the accelerations to little g because this is now a given, right? Going up, coming down, as long as it's a projectile where we can neglect air resistance and we're near the surface of the Earth, right? We know what little g is. And then I changed the x displacements to y displacements because it's going vertically. I also added some y subscripts here on the velocities, just to remind you that we're talking vertical again, and to separate it from horizontal when we get into a two-dimensional projectile motion, which comes after a couple of days of this. So what I want to do now is an example of using these kinematic equations to solve a one-dimensional freefall problem. Right? And then you're going to do some practice yourselves, right, with various concept builders and a worksheet. So, for some bizarre reason, we have a minivan on the top of a 221 meter tall building, and it falls off. All right, right? If you're riding in the minivan, there's probably a couple of things you want to know. One is, how fast are you going to be moving when you hit the ground? Right? What's your velocity as you hit the ground? Now, be careful with this question. It's not after you hit the ground, when your velocity, of course, becomes zero. It's as it hits the ground. So think of this as going the full 221 meters down, right? And then you find how fast you're going just before you make contact. You with me? Like 1 little millimeter above the ground. Okay? So be careful with that, right? And that's usually what they're asking for, because after it hits the ground, it's kind of a boring answer. Well, we're going to work this just like we did any kinematic equation problem. We're going to answer a couple of questions. First off, what do we need to know? What are we trying to find? Well, we're trying to find the velocity as it hits the ground. Is this the initial velocity or the final velocity? Because there's two of them, right? Two kinds. Yeah, it's the final vertical velocity. It's the final vertical velocity because it's happening at the end, yeah? Well, there's only one number in the problem. That's how tall the building is. So what is that for the motion of the minivan? Well, that's how far it's going to fall. So that's the vertical displacement of the minivan. But be careful. What direction is it going to fall? It's going to fall down. And down is negative. So in this problem, we are given the vertical displacement, but we got to be a little careful with the negative signs. There are a lot of negative signs in projectile motion because things are very often going down. Right? Sometimes they're going up and some things are positive, but still, right? When they're on their downward path, lots of negatives. Now, that's the only number in the problem. And if you remember, we need three things in order to work any kinematic equation to find the fourth thing, which in this case is the final vertical velocity. So what can we read into the problem? Well, first off, it falls off of the building. It's not like projected downward or thrown downward. So that means the initial vertical velocity is, it's zero. And if we can neglect air resistance, what else do we know now that we've done the two labs that we've done so far? We know the vertical acceleration is little g, the freefall acceleration, or the acceleration due to gravity near the surface of the Earth, of negative 9.8 meters per second squared, and don't lose the negative. Now, you might question whether or not this is a legitimate assumption to make, right? That we can neglect air resistance, because a minivan is a pretty big thing, but it's also really heavy, right? So, as we're going to find here, while it does get moving very fast, it doesn't take very long, and it's really heavy for its size. Fairly aerodynamic, right? Depending on what kind of how boxy the minivan is. So it's probably a decent assumption. It might be the answer we're going to calculate might be a little faster than it would be in real life, but would be in the ballpark here to neglect air resistance. So we're looking for the final vertical velocity. We know the vertical displacement, the initial vertical velocity, and the acceleration. So we have 4 kinematic equations. Which one should we use? The big hint here is what we don't have, which is the time. And there's only one equation that doesn't have time in it, and that's the 4th kinematic equation. Final vertical velocity squared equals the initial vertical velocity squared plus 2 times the acceleration times the vertical displacement. Well, the initial vertical velocity is 0, so the initial vertical velocity squared is 0, so that drops out. And I don't want to know the final vertical velocity squared, I want to know the final vertical velocity. So we have to take the square root of both sides. But here's a little problem. What's the square root of 9? Hopefully you said positive 3 or negative 3. Right? When you take the square root, you technically get the positive or negative root. Now, your calculator will always give you the positive answer, right? But we're in vector algebra, and positives and negatives are very meaningful here, right? Because they mean direction. So we need to remember that this is a positive or negative root, and then we need to choose which answer we want. Well, if this is the final vertical velocity, its velocity as it hits the ground, what direction is the minivan going? It's going down. So we want to choose the negative answer. Plug in our numbers. Note, if we had left off either negative sign, right, we would have ended up with a negative under the square root, which is imaginary. And although I made up this problem, we want a real answer. So that would have been, hopefully an opportunity for you to go back and figure out, oops, I missed a negative sign. If you get really sloppy, you make them both positive, but that's really sloppy. Sometimes when we get into AP, we might define a coordinate system where down is positive, just to make our life easier. A lot more positives that way. But if you do that, you really need to say that's what you're doing, right? So that the grader knows you're not just like forgetting everything that's negative. And if we run this through, we get, notice underneath the square root, we get a meter per second squared times a meter, which is a meter squared per second squared. You take the square root of that, you get a meter per second, which are velocity units. This negative outside here will make your answer negative, and it works out to be negative 66 meters per second. This is really fast. The conversion's about 2.2 to get to miles per hour. So you're talking 160 miles an hour or so. Right, so you're hitting the ground very fast. Very, very fast. Free fall here, falling with an acceleration, a constant acceleration of negative 9.8 meters per second squared. You get fast, very fast. Okay, remember the conversion is 2.2. This is roughly 10, right? So this is roughly like 22, it's roughly about 20 miles per second, every second faster, right? So after 1 second, you're going about 20 miles an hour. After 2 seconds, you're going about 40 miles an hour. After 3 seconds, you're going about 60 miles an hour and so forth. So you speed up. This is actually a very fast acceleration. Okay? You speed up very quickly. Again, watch the negative sign here when you take the square root of both sides. Now, a lot of times, to be nice, they might ask the question in a way where if you forget this negative sign, you don't get the problem wrong. They might say, how fast is it moving? Or what's its speed, right? Which is just how fast it's going, not the direction. If it's a multiple choice question, of course, you can tell by the answers whether or not they want the positive or the negative. But technically, if they say velocity, that is a vector quantity, and it needs a direction. You either need to say negative 66, or you'd have to say 66 meters per second downward. Okay? Part B, the other thing you might want to know if you're in that minivan is how long do you have till you hit the ground? Right? How long did it stay in the air? Which is, of course, the time. Well, what do we know? We know all the things we knew before. We know that the vertical displacement is negative 221 meters. We knew that the initial vertical velocity is 0. It's starting from rest. And we knew that the uniform vertical acceleration near the surface of the Earth is our acceleration due to gravity, which is negative 9.8 meters per second every second. Now, we also know the final vertical velocity, but it's a good problem-solving technique to not use what you found in Part A when you're doing Part B, if you can get away from it. This is why we have a set of kinematic equations, one of the reasons, right? If we can get away from that, because if you made a mistake in Part A, well, like let's say you forgot to square root, right? Well, if you use that number in Part B, you're going to get Part B wrong too. Now, I'm usually pretty good about giving you credit if I can see what you did wrong. But on a multiple choice question, you can't really see that, right? So best, if you can, to just use a different kinematic equation and don't use what you found in Part A. So is there a kinematic equation that relates the acceleration, the initial velocity, the displacement, and the time? And sure there is. The ever-popular third kinematic equation. Now this one is perhaps the most sophisticated mathematically, but in this case, it's not too bad because the initial vertical velocity is 0, which means the initial vertical velocity times the time is also 0. So if we want to solve for the time, we've got to multiply by 2 to move it to this side, divide by the g, and then take a square root of both sides because I don't want to know the time squared. Now, can you skip? Sure. You could skip from this step to this step if you are mathematically sophisticated enough. I certainly wouldn't mind. If you need to, do the steps, do the algebra. Now, technically, this is a positive or negative square root, but it's time, and we always want to go forward in time, so we always choose the positive answer. But just to be technical, anytime you take the square root, you get the positive or negative root. Plug in the numbers. Note again how if you had forgotten a negative sign on either one of these, you would have had the square root of a negative number, and that's not good. And if we punch in the answers, look at the units here. The meters cancel. So we have 1 over second squareds, which flip up to the top. So we have second squareds as our units. We take the square root, we get seconds. Right? So little indication that we were doing things right. And we get 6.7 seconds. Okay, so you stay in the air for a while here. Okay, but you don't stay in the air for very long, even off of a 221 meter tall building. So again, note our process here, just like we did with other kinematic equations. What are you looking for? What are you given in the problem? And a lot of times you got to read some things in. And don't forget, if you can neglect air resistance and gravity's the only thing acting and we're near the surface of the Earth, we know the acceleration due to gravity, that's a given in these problems. So that's another thing I don't have to bother to tell you in the problem. Right? Then you pick your kinematic equation and away you go with algebra. But remember, this is vector algebra. Right? So you got to do some things to make sure you get the right positives and negatives in the right places.